Hey guys, hi. This is Abhishek, Master Teacher of Physics at Vedantu, and welcome to this special video series where we are going to learn some crucial and important CBSE 10th concepts as well as numericals, problems, anything which you can go for. We'll also share some very crazy tips and tricks to actually score that 100% of marks to ace that examination, my dear students, which is going to happen in this March 2019. It's only 3 to 4, like basically 3 months left, and we thought why not help you guys with all these kinds of videos, isn't it? So in this particular new channel, if you guys have not subscribed to it yet, please quickly subscribe it right now, of Vedantu CBSE Class 10 channel dedicated for the CBSE 10th students. Remember that only 10th standard students will be giving you guys the content, otherwise no, and all of them are going to be free, you know that, right? Okay, great. Now since all the chapters are very important, we thought why not target the chapter which is kinda very important, and also a lot of students who face difficulties in that particular chapter. And that chapter came out to be, after a lot of surveys, came out to be magnetic effects of electric current. So this video series is start writing from the chapter how to score 100% of marks in magnetic effects of electric current. That's the topic we are going to cover, and this chapter we are going to cover it completely, like all the important questions, all the formulas and everything. We are going to cover it up. Now after this, we did a quick survey again, and we found out that the first topic where a lot of students actually face difficulty is nothing but the electromagnetic induction. Because DC motor, AC generator, questions are straightforward, correct? No, from this chapter straightforward. Draw the parts, working principle, explain the parts, something like that. But in the case of electromagnetic induction, there is a lot of questions which are kind of twisted. They will ask you the direction of current, they will ask you the direction of magnetic field, and so on and so forth. So we thought, why not start this particular video series with a bang where we can help all the students out there. Okay? So without spending any more time, let's get into it right now. I would require everyone's complete attention here. I want you to focus right now. Okay? So I would like to show you guys that after this particular video of just 20-25 minutes, what kind of questions you will be able to solve. So oh my god, yeah, so this is the kind of a video this is the kind of the question which you will be able to solve right now after this particular completion of the video. Very simple questions. This might look pretty confusing right now. I would not read it out right now, but I would be reading it out at the end. I would like all of you guys to have a really good look that this is what you're going to solve. And this question right now, my dear students, comes for 5 marks, where they would ask you explain why the deflection occurs in the galvanometer in that particular coil. Number 2, does the direction of the current is in clockwise or anti-clockwise direction? Number 3, state the observation of galvanometer if magnet is moving towards the coil or when the magnet is moving away from the coil. All the questions for electromagnetic induction, but a lot of students have no idea about it. And one of the important questions at the 4th part, that is nothing but state the observation in galvanometer when both the coil and the magnet are moved together. Some questions of that particular sorts also happens to be a part of hot questions, which is nothing but higher order thinking skills questions. So here it guys, after the end of this video, you are going to solve that in seconds. Let's start it. I would like to start this session with a very interesting question. Who discovered the concept of electromagnetic induction? I believe all of you guys would know the answer. Option A, Hans Christian Ørsted. Option B, Alexander Fleming. Option C, Michael Faraday. Or option D, James Clerk Maxwell. And what do you guys think is the correct answer for this? I'll give you exactly 3, 2 and 1 second. Your time is up. Let's see how many of you guys got it correct. Is the correct answer, my dear students, is Michael Faraday. Michael Faraday is the person who is also known as the father of electromagnetism for a reason, because he himself discovered it. Let me show you that guy. Let me show you that guy. That guy looks like this. He's Michael Faraday right here, and he's the guy who actually destroyed a lot of students' life, including the teachers as well, because we have to teach this. I'm just kidding, guys. So here is the guy who actually gave this phenomenal phenomena. So what did he say? He said a very interesting thing. Let me show it to you in a very descriptive way. Okay? We'll not define electromagnetic induction right now, because that too is there given in your textbook. That too everyone does. We will try to understand from the core of the topic, so that any kind of a question which you get in CBSE 10th, you are bang on it. isn't it? That's what you want. That's what you're giving it to you. Here is the setup. So this is the initial setup of Mr. Michael Faraday. He said a very interesting thing. First of all, he has two experimental equipments, as you can see very clearly. One of them is a circular loop or a coil, which you can study in the chapter. And then also you have a magnet, about which the entire chapter is about. So you have a coil and a magnet. What did Mr. Michael Faraday did? Michael Faraday connected the coil with the galvanometer. Not with the battery, but with the galvanometer. I believe all of you guys know what is the purpose of a galvanometer. I believe all of you guys know. It's nothing but to detect the electric current in the coil, if it is there or not, isn't it? So right now the galvanometer is at zero deflection because there is no current flowing, there is no battery connected to it, hence no current flowing. Next, what he did do? He took up the magnet and kept near the circular coil or kept near the circular loop. And what did he observe? What do you think he observed? Nothing. He observed nothing. He could see that the deflection is still zero. So he understood that when I have a magnet near to the coil, there is zero current produced in the coil. That's what his hypothesis. Can I induce a current in a wire or a coil with the help of a magnetic field? That magnetic field which is produced by the magnet, because as we know, magnetic field will be produced by the magnet right here, and this magnetic field will get linked with this coil, as mean they will come in contact, and this magnetic field start producing a current. That's what Michael Faraday thought, but that didn't happen. Obviously, the galvanometer didn't show any deflection. So he thought, what next? So my dear students, he thought instead of keeping the magnet stationary, what would happen if I start moving the magnet? And that's what Michael Faraday did. He went on to proceed and he started now moving the magnet, and then he saw there is a deflection. Galvanometer started showing deflection when the magnet is moving. Then he concluded one very important statement, which all of you guys have to keep in mind right now, that for the magnetic field to create a current in the coil, the magnetic field must be changing. That is the key word which Mr. Faraday caught. Only a changing magnetic field can create or can induce current in a circuit. Otherwise it cannot. Now if you notice, now let us try to understand this entirely. Okay? Now focus here very carefully. The magnet moves towards the coil, deflection, but when it's stationary, no deflection. Moves away from the coil, deflection, but when it's stationary, no deflection. Comes again near, deflection again, but now again it will show zero deflection because it's stationary. So what it means, that doesn't matter if the magnet is going away or coming closer, it will not matter at all unless the magnetic field is changing or not with respect to the coil. As you can see, when it is coming closer, magnetic field changes with respect to the coil. When it is going away, again magnetic field changes with respect to the coil. That induces a current in the circuit or in the coil. But that is not electromagnetic induction yet. We have not reached there, but I hope you guys have got this particular point. It doesn't matter if the magnet is moving away or closer, current would be generated, because in both the cases, the magnetic field will change with respect to the coil, isn't it? Now moving forward, and let's try to understand the same procedure with the help of a very interesting graph. The magnet is coming closer, you can see the current started increasing. One second. The current started increasing in the coil. And then what happened? Now the magnet is going away. So current started increasing, but in the opposite direction, isn't it? The current started increasing in the opposite direction. Look at it again. The magnet is coming closer. Current slowly increases in the coil, increases in the coil. Now it takes a heat because it's not the closest. But when it's inside, the relative velocity between both of them is zero. Relative velocity. So it means with respect to the coil, the magnet is not moving. And with respect to the coil, if the magnet is not moving, that would mean the magnetic field is zero. I believe that many of you guys might not be understanding this concept. Let me make it very simple for you. Let me make it very, very simple for you. So let's wait till the magnet is inside. Okay, the magnet is inside the coil, isn't it? So now when the magnet is inside the coil, think about the magnetic field. The magnetic field will be like this. It is entirely covering the coil. Okay? So that means continuously throughout the process, the magnet is inside the coil, starting right from here to moving here. The same magnetic field is linked to the coil. Same magnetic field. There is no change in the magnetic field. Hence, when the magnet is inside the coil, the current is zero, because there is no change in magnetic field. As soon as it will start going away, the magnetic field will start changing with respect to the coil. Correct? Isn't it? I believe you guys got that point. Look at it very carefully again. Magnetic field, increasing, current increasing. Now became constant because magnetic field is not changing. Now magnetic field starts changing, and you got a negative current. That's it. So this is what was explained by Mr. Michael Faraday. But I would just like to ask people who are watching this a very simple question. Think in this way. If the magnet is stationary and I'm moving the coil, can that will still produce current? Give me that answer in the comments down below. Cool? Give me that answer in the comments down below. Whether is it necessary only the magnet should move? Can the coil also move to give me the current? Give me that answer, guys. I'm waiting for that. Okay. Now let us move to the next question, which is very important. So I would like all of you guys to keep in mind what did Faraday said. And let's try to understand what about one more scientist. This is the question. Who created the link between electric current and magnetism? Option A, Hans Christian Ørsted. Option B, Alexander Fleming. Option C, Michael Faraday. And option D, James Clerk Maxwell. Now I would know that you might go for Michael Faraday because word magnetism is there, but the question is the link between electric current and magnetism. He was the founder of magnetism. Electric current was found by Andre Ampere. But who created the link? And the link, my dear students, no one else but Hans Christian Ørsted discovered. And this is the guy with whose experiment we start the chapter magnetic effects of electric current, isn't it? So that's what we're going to cover it for. This is the guy with Michael Faraday who did this. Now what did he say? He said a very interesting thing. Michael Faraday was doing the opposite thing, that he was trying to tell us that when magnetic field is there, that might create an electric current when it is changing. Same thing Ørsted said, but at least 50 years before Michael Faraday. He said in the opposite way. He said that if I have a circuit, as you can see in front of you, if I have a circuit, very carefully look at it, and that circuit is connected to a battery, the battery must be providing current, and the battery provides current to the coil. And when this electric current starts flowing through the coil, this would generate a magnetic field around the coil. So what did he say? He said a very interesting statement that electric current or electric field can generate magnetic field. So he said the same thing, but in the opposite way as compared to Faraday. Faraday from magnetic to electric, Ørsted is telling from electric to magnetic, it's possible. You don't have to change anything. You just allow the current to pass through in the coil and it will give you magnetic field. This is pretty interesting. All of you please understand it, because that would mean each and every wire surrounding your house, the mobile phone you're holding in your hands, the laptop through which you're watching this video, each and everything have their own electrical wires. And if there are electrical wires like this same coil, it must also be producing magnetic field. Yes or no? Definitely does. That's very extrusive, right? Exactly correct. So this is what his statement was. And obviously, to just conclude it, since it's producing magnetic field, it is obvious it is acting like a magnet. Obviously, no, it's producing its own magnetic field. That's what magnets also do. Magnets also produce magnetic field. This is also producing its own magnetic field. Hence, it's a magnet. Since it's acting like a magnet, this coil also must have a north pole and it also must have a south pole as like a magnet. Correct? So one face will be north pole and one face will be south pole for this particular coil. As simple as that. Now let me take you guys to the next very important concept or a question, or this is the very crucial point. This is the turning point of this video, because now I will bring in Ørsted's experiment and then combine with Michael Faraday. You see in front of you guys a very interesting thing. Look at this very carefully. This is Ørsted's coil. Okay, because I'll tell you why. There are two coils which you see in front of you. One is coil A and one is coil B. Correct? Coil B is called as the secondary coil as there is no battery and it's only have galvanometer, and this is called as a secondary coil because an induced current would be generated in it from the primary coil, which is the coil A. This coil A, my dear students, as you can see, is connected to a battery and current is passing through it. According to Arrested, what should happen here? According to Arrested, this current carrying conductor or the coil must produce its own magnetic field. It should have a north pole, it should have a south pole. That magnetic field, when it gets linked with this coil, as you can see, you see that current starts flowing, magnetic field got linked to this particular coil, and that started showing deflection due to the inducement of the electric current. So what we have done nothing. We have taken off the magnet and we have put a coil which acts like a magnet. And this, my dear students, is called as electromagnetic induction. I believe you guys got that. Now let me put it in a very simple way. When we have two coils, coil A and coil B, coil A called as the primary coil, coil B called as the secondary coil. Coil A is connected to the battery, coil B is connected to the galvanometer to detect current. When current starts flowing through the coil A, it produces its own magnetic field, and when this magnetic field gets linked with the coil B, an induced current is being generated in the secondary coil, and this is called as electromagnetic induction. But it doesn't end there, because I would like to ask a very interesting question to you guys. Here, Faraday said the magnetic field must change and then only the current will be produced, otherwise it will not change. And for that to change, the magnet should move. Here the coil is not moving. What do you guys think then how it is being produced? What is your answer? Think. I'll give you 3, 2, and 1. The time is done. I believe you guys must have thought about it. People who observed it carefully notice the switch is being turned off and turned on again and again. Due to that, what happens? Switch turned on, current started flowing, magnetic field started. Switch turned off, current stopped, magnetic field stopped. On, off, current not there, current not there, magnetic field there, magnetic field not there. So magnetic field is now changing. It's there, it's not there, so it's changing. This constitutes a change in magnetic field which is induced in the coil. Now guess, ठीक है, ये तो एक तरीका हुआ. Now guess, I will tell you that it is possible to create this change even if the switch is continuously turned on. Even if when the circuit is completely closed throughout the time, it is possible to create that change in magnetic field. Can you tell me the reason? How can that happen? If you can do that, you're pretty brilliant then. Come on, think. You can do it. I'll give you 3, 2, and 1. If you guys have done it, you are pretty smart then. I'll tell you the answer, how to do it very carefully. I'll tell you. It's pretty simple. I'll turn on the switch and instead of a battery, I'll connect this coil directly through a major power source of AC current. What is AC? AC is nothing but, as you know, it's nothing but alternating current, isn't it? And what does an alternating current do? Alternating current is nothing but which changes with time. It changes with time. Hence, if alternating current is present in this coil, it will change with time. That would mean the magnetic field produced by this primary coil will also change with time because it is dependent upon the current. So when this magnetic field keeps on changing with time, that would mean that the secondary coil will now be induced with an electric current. That's it. If you guys were able to think that, you guys are smart. You are smart. Okay, so I believe you have got that particular point. Now moving to the very interesting question, again a CBSE 10th question which I would like to ask all of you. If a south pole is approaching a coil, then the direction of the current at the coil end is. If a south pole instead of a north pole is approaching a coil, then the direction of the current at the coil end is what? Clockwise, anti-clockwise. Now this must be a very, very confusing question for you because you don't know what is the relation between south pole and what is the relation between direction of current, isn't it? You have no idea. That's why we have a very interesting concept called the clock rule, where pretty interesting. Completely focus here, you will understand. Remember I told you, if you have a coil and it's a current carrying coil, it must have magnetic field according to arrested, and if it has magnetic field, it must have poles also, north pole and south pole. So if in case the pole is north pole, then that would mean that that end of the coil has anti-clockwise directed electric current. That the electric current flowing through that part of the coil is anti-clockwise. How to remember this? Pretty simple. You create a north pole and this end looks like anti-clockwise direction, isn't it? Look at it carefully. I know my diagrams are pretty good. Just kidding. So yeah, north pole, simple. So north pole, anti-clockwise direction. This can be reversed also. That means if I tell you there is an anti-clockwise current flowing through the coil, that would mean there is a north pole there. This could be reversed also. That's what I mean to say. So now you have similarly south pole. South pole is even more simpler. You have south pole. So if you have a south pole at the end of the coil, then that south pole must give you a clockwise directed current. South, no, S looks like clockwise. So you can remember this in this particular way, and that is called as clock face rule, and it's very important not only for 10th standard, it's very important for 12th standard, it's very important for JEE mains and JEE advanced also. So keep that in your mind. So now let me ask you guys the same question again. Before I ask you the same question again, there is one very interesting thing which I need to tell you from the 12th standard. This question is pretty important. And it's not only important from the 12th standard perspective, also important from the 10th standard perspective, but it's apparently not in your syllabus. Lekin questions related to it sometime being asked. So what we do, we'll learn this so that you don't lose that marks. Here is a guy called as Chris Lenz. Chris Lenz said a very interesting thing. He said, an induced current in a circular coil or a circular loop will be moving in that circular loop in a way that it will oppose the cause which produced it. I know it might be a very confusing thing for all of you. I'll draw it and show it to you. So, see, you have a coil connected to a galvanometer. You have a magnet, north pole here, south pole here, moving towards it. Isn't it? Now when the magnet is moving towards it, what would happen? Magnetic field linked with this coil, if I take a different color pen, yeah, the magnetic field linked with this coil will now keep on changing, hence this particular coil will start generating a current, will start having a current, obviously. So this is now induced current. Now Lenz states that this induced current will be in a way that it will oppose the reason caused it. What was the reason this induced current was produced? This induced current was produced because the north pole of a magnet was coming closer to it. So the current produced here will be in a way that it will be opposing this motion. It will now reflect back, or it will now repel the north pole's movement. So for that to happen in this coil, naturally poles are generated, because when the induced current is being generated, that would create this magnetic field for this particular coil also, because जहां भी current है वहां magnetic field है, तो यहाँ पे induced current की वजह से एक magnetic field produce होगा, और जैसे produce होगा कि इस area में, in this particular region of the coil, it would be a north pole. So that when this north pole is coming towards the coil, it's now deflected away. The coil is trying to repel the north pole back, opposing it. That's what Lenz said. I'll repeat this statement again in a very simple manner. Lenz said the induced current being generated in the coil will be in a way that will oppose the reason what actually caused it to happen. So the reason here was that the north pole was coming closer to the coil. The coil is now having a north pole at the same end that opposes the coil to go through. Now think and tell me, if there is a north pole at this particular end, what is the direction of current in this particular end of the coil? You know the answer. North pole means anti-clockwise direction according to clock rule. Now my dear students, answer this question. If a south pole is approaching a coil, then the direction of the current at the coil end is what? If the south pole is approaching the coil, to oppose that, the coil must have a south pole at that end, according to Lenz law. And what do you mean by south pole? South pole means clockwise direction. South, no, S, clockwise. Baat khatam. That's it, my dear students, and now you are completely ready to answer all the questions from this particular part. Shall we test it up? I believe you completely, and you are well capable of answering each and every question here. Let me prove it to you. So I'll try to explain you the question. There is a coil and there is a magnet. The magnet's north pole is moving towards the coil, as moving towards the right, and the galvanometer shows a deflection towards the right when the north pole magnet is moving towards it. Obviously, because of electromagnetic induction, an induced current is being generated in the coil, and this galvanometer is showing a deflection for obvious reasons. We understood that. Now the question states, explain why the deflection occurs in the galvanometer because of electromagnetic induction, which we all know as the definition. Number 2. Does the direction of the current in the coil appear clockwise or anti-clockwise when viewed from end A? This is your end A right now. What does it state? North pole is going towards it. So according to Lenz law, there must be a north pole created here which can oppose the motion. So north pole ripple. North pole hai to kaun sa current ka direction hoga? Clockwise or anti-clockwise? You know the answer. It's definitely going to be anti-clockwise. Answered. Next question. State the observation in galvanometer when the coil is moved away from north pole. So now, this is the north pole, and it's been stated that the coil is moving away now and the magnet is stationary. So when the magnet is stationary and the coil is moving away, yani kya hoga? Jab, it's the same scenario. Either you keep the coil and the magnet, keep the magnet stationary, move the coil away, or you both keep the magnet and the coil stationary and keep the magnet away. Both means the same thing, isn't it? So initially the magnet was coming closer and the galvanometer deflected towards the right. So now when the magnet is going away, what should happen? It should also show a deflection right now because there is a change in magnetic field, but as we studied earlier, it should show me a different direction. Deflection, but in the opposite direction. Because previously it was coming closer, now it's going away. So this must be indicated visually, and that's the answer. Moving to the last question, one of my favorites. State the observation in galvanometer when both the coil and the magnet are moved to the right at the same speed. Isn't that a very interesting question? I'll allow you to read that again. State the observation in galvanometer when both the coil and the magnet are moved toward the right at the same speed. Listen to it and understand very, very carefully, guys. That would mean coil, magnet, both are moved towards the right, the same speed. So now my question is, aren't they both stationary with respect to each other? For example, when we all are moving in a bus, there are two buses, together there are two buses, both of them are going at the same speed. For both of us, we will feel, if you are sitting inside the bus, we will feel that both of us, the relative velocity is 0. For both of us, it feels that we both are stationary. So for this coil and the magnet also, the same thing will appear. It will feel like they both are stationary with respect to each other. There is no change in magnetic field because this personally or this personally is not moving. So what should be the deflection of the galvanometer? Since there is no change in magnetic field, the galvanometer shows 0 deflection because there is no induced current. That's it, my dear students. That's it. And after that, I would like to tell all of you guys a very interesting thank you to all of you for watching this video. I hope this video helped you guys a lot. If it really did, please hit that like button and subscribe to this channel right now so that you can get the benefits of all these videos launched specifically for all of you guys, especially for all of you. Okay, so that you can score that 100% of marks. So this is just the first video. We'll be launching a series of videos for all the chapters for physics, mathematics, and if possible chemistry as well. Okay, so that you guys can get all the benefits from Vedantu from this particular site in perspective of the examinations. Got it? Now, in this starting, as I told all of you guys, this topic was chosen basically because I did a survey with all these students and I understood that this topic is very important for them and very confusing for them. That's why I took it up. So if you guys need any other topic to be taught, Put down in the comments right down below. You people, students who are regular to me, they know that I personally reply to all the comments. So put down in the comments down below that which topic you want me to take next in the chapter magnetic effects of electric current, so that I can take it up for you and help it out. Finally guys, again hit that like, share and subscribe button. Until the next video, this is Abhishek signing off. Enjoy your life.